This is probably the most important video of the semester. Okay. This is going to apply in a lot of other modules, so I really want you to focus here. This is how we do calculations when we don't have equilibrium values, right? The ones that we just did in the previous video were super easy. It's plug and chug, solve for where you don't have, easy to do. Now, the problem is a lot of the times it's hard to get concentrations at equilibrium. You mix your stuff together, and then how do you determine what the concentrations are now at equilibrium? Well, unless it's a colored solution and you can use a spectrophotometer, we actually can't measure those. So how are we going to get there? We're going to use a tool that is called ICE tables. Okay, my motto for the semester is when in doubt, ice it out. If you're not sure, draw an ICE table. But again, you have to read very carefully for things that are at equilibrium or things that are not at equilibrium. So read your questions carefully. Okay, so ICE tables can be used to solve for multiple equilibrium concentrations. So if I'm missing like a couple of them, can't just plug and chug into a K equation if I have two or more variables, right? ICE tables can be used to find Kc or Kp. If I maybe didn't give you the equilibrium concentrations, I only gave you the initial concentrations. I can't just plug and chug if I gave you initial, because initial is not at equilibrium. So if you plug them in, you're not going to get the K value. So these types of problems are going to be your most common types of problems this semester. So what does I stand for? Well, I stands for initial. That's like the beginning, how much stuff I put in. C stands for the change. How much is it going to change by? And E, of course, stands for how much there is at equilibrium. Okay, so I'm going to kind of elaborate on these. So initial is what you start with, or in quotes, put in a reaction. Change, the amount it changes by is going to be stoichiometric, right? You look at a reaction, I'm going to scroll up, for example, this reaction. 1 mole of this reacts with 3 moles of this to make 2 moles of this. That's how it's changing, the ratios that is changing with. So the change is stoichiometric. This is the amount that is like reacted or changes, again, is stoichiometric amount that is used or made. This is stoic. Okay, stoichiometric. And then the amount at equilibrium is, of course, equilibrium. So once it's reached equilibrium, remember the concentrations stop changing. Those are the amounts we're looking for. So this is amount at equilibrium. Okay, and I'm going to show you how to set it up, how to get from initial to equilibrium if we do not have those equilibrium values already. All right. One key thing I need to point out is anytime you use an ICE table, you have to be using your data in either molarity or pressure. If it is not in molarity or it is not a pressure value, you cannot plug it into an ICE table. So I'll say this multiple times, molarity or pressures, that's what's going to go in there. So here, let's fix this real quick. There, we got that. Molarity or pressure. And the other thing is, this is the most important part of the table because equilibrium concentrations can go into K expressions. Initial concentrations can't. That's why reading your problem is going to be important. These go in your K equation. Okay, no other values. Now, again, before we go set up these what are called ICE tables, whenever you're looking at a generic reaction, so let's call it A makes B. Usually when we do a reaction, we start with reactants, we put in a bunch of A, and then it's going to make B to get to equilibrium. Okay, so A, the amount of A is going to decrease, it's going to get used up while B is being made. So A usually decreases and B usually increases. Okay, so we're talking about how much it changes by. A is going to be used up and B is going to be made. Again, this is most of the time, not all of the time, but most of the time. And so I'm going to set up an example with you. This is a very simple, straightforward example, but it should be kind of a template for all of the equilibrium examples that you're going to do from here on out. Okay, so this is a really good key example. So suppose I've got a 4-liter flask that has 0.2 moles of N2O4 initially added to it. So this is not an equilibrium. Now, if I had the equilibrium values of this and this, I could plug it into K, but I don't. So this is how we set up an ice table. This initial thing tells me I need ice. The fact that I don't have equilibrium concentrations, I don't have K, this tells me I need to set up an ice table. So this is how you set it up. You have your equation, okay? And then we're going to make it like a table. I, C, E. You want to separate all of your substances. Okay, and we should have a box for I, C, and E for all. Okay, so initially, what do I have initially? Well, initially I have 0.2 moles of N2O4 in this flask. Now remember, I said you have to do molarity or pressure when you're doing an ice table. So the molarity of N2O4, I have to actually calculate before I plug it in. So I've got 0.20 moles over 4 liters. So that is 0.05 molarity is what I'm starting with. Okay, now that's all that I put in there. If I don't mention anything else, it gets a 0 initially. I didn't put in any NO2, and that's because I just started with reactant. It's going to turn into NO2 to reach equilibrium. Okay, so let's make a little note of that. None if not mentioned. Okay, so if I say nothing in the problem, there isn't any. All right, now the change values, how much does it change by? Remember I said this is stoichiometric. This is where our mole ratio is going to come into play. This is a 1:2 ratio. So anything this decreases by, this is going to increase by twice that. So the way that we represent this is with X. So if this decreases by X amount, so let's say minus X, it uses up a certain amount, then that means I'm going to make, so this one's going to be plus twice that, 2X. Okay. So it's almost always going to work out that the left side of your reaction is going to have negative X's because that stuff is being used up. And the right side of your reaction is going to be positive. You are going to be making something. But again, it is stoichiometric. So whatever this decreases by, this increases by double that. Okay, so for our notes, we'll say we're going to use X. So your change should always be in the form of X something. Okay, and coefficients. Okay, if it's negative, that means you're using it up. It is decreasing in amount. So negative if you are using / decreasing, this is usually the reactants, not always, but usually the reactants. And positive is producing or making. Producing. I'm using producing because it's the products. Okay. So usually the negative is the reactants and positive are the products. Okay. Also, if we started with 0, I can't use it. I don't have any, so it can't go negative. You cannot have a negative molarity. So if you did something and you end up with a negative molarity, you did it wrong. Go back and look at your changes. Okay. I'm happy to help. So negatives for using and positives for gaining. So now, what is equilibrium? Well, equilibrium is what we kind of settle out at, right? So all you have to do is add your initial and your change together. So this and this is going to give me 0.05 minus X. And this one is going to be 0 plus 2X. So that is just 2X. So the equilibrium row is I and C added. Okay, so at equilibrium, I will have 0.05 minus whatever X was. And at equilibrium, I will have 2X, whatever X is. Okay, so this is the first thing you want to do is set this up. Okay, so this is going to be our number 1. Set up your ice table. Now, anytime you have an ice table, number 2 is going to be to set up your K equation. All right, so set up an ice table, set up a K equation. Well, the K equation for this reaction right here, products over reactants, So it would be NO2 squared over N2O4. That should be really easy by now. Okay, I just wrote products over reactants with my exponents. And then I can plug in, well, I guess it kind of depends. So once I get to this point, all of your problems are going to look like ice table, K equation. Okay, once you get to this point, since this is our equilibrium constant, you can plug these equilibrium values here. I'm going to use a different color actually. You can plug these equilibrium values into your K equation. So this can go here and this can go here because those are your equilibrium values. Now, once you've done that, then we can use whatever other information I gave you in the question to solve the problem. So once I do that, I'm going to plug them in. So kind of step number 3, I guess you could say, looks like this. K is, I'm going to plug in my terms of X. So that is 2X, still squared. Okay, just plugged it in there. And then this one is 0.05 minus X. So now I have everything set up equilibrium wise. If I have a problem where I gave you the K value, now I could plug in K and solve for X. If I have a problem where I gave you an equilibrium concentration, we can plug that in and solve. But this is going to be like your general setup for every equilibrium problem. Okay, so I can't solve this one because I didn't actually give you any more information, but this is your like go-to setup. Okay. Now the solving, okay, so once I get to this equation, how do I solve for things? What do I use? And this is where another piece of information is going to come in. Okay, so the solving of your ICE problems. Once you have your K equation set up and you substitute in your X values, you can solve for whatever it is. Now, like I said, it depends on the information I gave you. Do I give you K? Do I give you something related to X? Depends on the problem. So we are going to set up number 7 together. And then I do have more practice after this for you to try to do it on your own. So we're going to do number 7 right here. Now, for the decomposition of SO3 at 1000 Kelvin, remember, we're not changing the temperature right now. I don't actually need that temperature. It's just, I have to say it because I'm keeping it constant. A 2-liter vessel is initially, that's an important word, charged with 0.012 moles of SO3. So that is initial. Okay. Next sentence, if at equilibrium, so this is a different place. At equilibrium, it is found to contain this many moles of SO3. All right. It says then what is the value of the equilibrium constant? Well, first of all, I know I need to make an ICE table. Not only because I don't have all the equilibrium concentration. So like if I had all 3 of these, I could just plug them in and find the equilibrium constant. I don't. I have the value of SO3 and that's it. So I can't plug it in. Also, anytime you've got some initial information, probably going to need to make an ICE table. Okay. So this tells me ICE. Okay. I need an ICE table. So I'm going to go ahead and set it up. All right. I've got my equation here. I'm going to rewrite it so I can kind of spread stuff out a little bit. I got 2 SO3 makes 2 SO2 and O2. And then I go I, C, E, doop, doop, doop. And then you separate each substance. Okay. Now they're all gases, they're all included, they're all important. So I'm going to put in the information that I do have for my ICE table. Let's see, I have 0.012 moles of SO3. So I'm going to have this information, but it has to be in molarity. So I'm going to do 0.012 moles over 2 liters. So my starting molarity is 0.006 molar. Okay. Now, initially, I said initially charged with, that means like that's what you put in it. It's just a gas, so we use the term charged with this. That's it. I didn't mention that I initially had anything else, so these get 0. Okay. Now, if you look at this reaction, I've got some of this. So I'm going to be using up some of my reactants and making some of my products. So this is going to be a negative something X, and these are going to be positive. Again, it's usually going to be that we are using up reactants and we are making products. The only time that wouldn't be the case is maybe we started with some of everything, You won't see that happen a lot. Or maybe I started with all products, then it would go the other direction, but this is usually how it's going to be: negative reactants, positive products. Now remember, the change row is stoichiometric, so we have to take into account our coefficient. So this is going to be minus 2x, it's going to be plus 2x, and this is going to be plus x. That's going to take care of the stoichiometry. And then I add down. So this is 0.006 minus 2x. This is 2x, and this is x. Okay, step 2, make my K equation. So K looks like this, products over reactant. So SO2 squared. Sorry, my pen is not cooperating right now. SO2 squared times O2 over SO3 squared. Now I can plug in all of these things into their respective places over here. Okay, so let's see. SO2 was 2x. So now if I rewrite it this way, so 2x squared times O2 is just x, so x. And then SO3 squared, this is SO3. So I'm going to 0.006 minus 2x quantity squared. All right, so this is my generic setup. I'm here. Now, how do I solve? So if we kept reading, it says if at equilibrium, that's the part we're going to use now, the vessel is found to contain 0.0048 moles of SO3. So I'm going to switch colors because I'm at equilibrium now. I know at equilibrium, I now have that my SO3 concentration is, again, I'm going to go ahead and put this into molarity, is, sorry, you can't see that, 0.0048 moles. It's still in this 2-liter container, so I'm going to calculate it like that, and it is 0.0024 molar. So what that means is that it started at 0.006 molar, now I'm at 0.0024 molar. So what I can do is say, well, if this is what I have at equilibrium, this is equal to this. And then I can solve for x. So that's how I'm going to solve for x in this problem. Okay, so I'm going to do 0.0024 equals 0.006 minus 2x, because those are both equilibrium values. All right, so I'm going to subtract, divide by -2. I get that x is 0.0018. Now I can plug in that x to this whole equation and solve for K. I'm trying to find my equilibrium constant. So I'm going to get that K is 2 times 0.0018 squared times 0.0018 squared. Okay, and then on the bottom, 0.006 minus 2 times 0.0018. And that's squared. So be very careful with your parentheses, what's squared, where the x is going. Make sure you can do this in your calculator. You should end up with that K is 0.00405. And remember, equilibrium constants don't have units. They're just values that show us kind of the ratio of products to reactants. All right. So make sure you can plug that in. This is one way in which we solve for K, and I will do some other ways in the next video.